to our speakers today. We have Mr. Sho Nakamura from our partner NoiseKen. We have our colleague Romy Salame, sorry. Romy, she is application engineer, and we have also Thorsten Arding, he is solution architect with Zuken GmbH. Over to you, Romy.
Thank you, Ursula, for the very warm welcome. Okay, so first of all, I will start with my presentation by going over the agenda. So today we'll explore how to enhance PCB design by using Zuken's CR-8000 software and NoiseKen measurement tools. First, I'll be introducing CR-8000 as a comprehensive tool for every design stage, from schematics to signal integrity analysis. Then we'll look at how CR-8000 integrates with NoiseKen's measurement equipment to validate designs with real-world data. After that, Mr. Sho Nakamura will follow up with a live demonstration showing NoiseKen's role in refining PCB designs during testing. And finally, we'll recap the main points and have a Q&A discussion to discuss any areas anyone would like to explore or address any further. So first of all, this slide illustrates the overall workflow, showing how the design process in CR-8000 seamlessly integrates with prototype measurements using NoiseKen. On the left side, we have the PCB development process using Zuken's CR-8000. This begins with schematic design, followed by floor planning, routing, and then moving through steps like panel creation and DRC checks, which are very crucial for ensuring our design meets necessary constraints and standards. And then at each stage, CR-8000 offers powerful tools such as constraint management, signal and power integrity analysis, and the MC Advisor to optimize design quality. I'll be going into more details on a few of these features shortly. On the right side, we see how the design data transitions to prototype measurement using NoiseKen's equipment. After the PCB is manufactured and mounted, the prototype goes through inspection and validation phases. Here, NoiseKen allows us to collect real-world measurement results, helping us identify real-world issues. These results are then fed back into our software CR-8000, allowing us to refine the design based on actual measured data. Now let's look at the design gateway with CR-8000. This tool allows us to design and organize PCB schematics efficiently. We can assign simulation models automatically or interactively and generate waveforms directly from the circuit design, helping us understand the behavior of signals early in the design process. In addition to that, standard or custom topologies can be set for signal flows. Another key feature is the ability to conduct what-if analysis, which lets us explore various scenarios to optimize signal integrity before moving on with our design. And finally, once all the all the signal rules and topologies are set, they can be seamlessly forwarded to design force or exported into various formats for further use. Now, to give you a clearer picture, I'll play a brief video which shows some of these features in action. In the video here, we can see components are being placed on the schematic sheet. Now we have all the components placed. We can see here the simulation models are assigned, and we can see the different connections, such as the power and ground connection, VDD and ground. You can see it over here. We can also see the components being connected. Here we have the whole design connected with 2 sheets. And we can also see here, for example, the BD and BA bus lines. Now we open the constraint browser and we have all the signals and models that we made in our design, all of them organized in one place. And I will be talking about the constraint browser in the next few slides in more details. Now we make a custom topology. We can choose the signal type, topology type, and how many buffers we have. In this case, we're just doing a simple single signal with 2 buffers and 3 transmission lines in between. And for each transmission line, we set a minimum and maximum length, and we save the topology. Once our design and all the rules are done, we can forward the design with all its rules and topologies to design force. Now let's look at the routing tool in design force. First, this tool provides a single environment for both automatic and interactive routing, allowing designers to work efficiently. A standout feature is its dynamic routing for differential pairs and buses. This helps maintain the required symmetry, which is crucial for high-speed performance. It also offers tight skew control, ensuring signals arrive at their destinations at the right time, which is essential for high-speed applications. The system also allows for automatic and interactive tuning of nets based on specific design rules and topologies, making it easier to meet performance goals. And lastly, we have the Active 45 router, which lets us route with just a single click following our cursor's path. This makes the design process smoother and faster. Now, after Design Gateway, we have all the elements forwarded as they were connected in the Design Gateway tool. We can see the connection or the gray lines, and this makes the routing process way easier. Now we have this signal, which is being manually routed, and it shows just how easy routing is. So just from one pin to the other. And then this signal will be being automatically routed, and we can see the efficiency of the automatic routing feature. We just choose the 2 pins and it automatically routed it. Now moving to the topology routing feature, we have a specific signal we want to route. So we go into the constraint browser, and then we select the topology that was created in the design gateway. Now we assign the components. So we have here this IC, we assign it for the first node, and the second one is assigned. And then we apply the topology. We can see here all the details of the topology, such as the pin pair length, routing width, and the impedance range. The topology is also displayed on the connection, making it easier to route. For another signal with 3 buffers, we also load another pre-made topology, which we have over here. And also all the details are there. Now you'll notice the constraints for the signals and topology are marked by the tilted squares. And now we can see when we move into them that the impedance requirements are being met. And then we place it over here. Now we begin routing the signal following the topology, which, as a reminder, it includes 3 different transmission line widths. So we put the first one, this is the second one, and then we finish it. And now we apply the constraints, apply the rule, execute. And now we can see the width for each section different. So here it's 0.1, here it's 0.127, and back to 0.1. And each section change according to the constraints we've set. Now we open the constraint browser again and choose our signals, which are already routed. We already routed them. And we check for the routing. The match ratio for the impedance is 100%, meaning the impedance constraints are all met in the range specified. However, for the pin pair, with the length isn't matching the constraint yet, so most of the connections are shorter than they need to be. And to fix this, it's very simple. We use the lengthening function, which automatically extends the transmission lines into an S shape. So as we can see here, the S shapes, we can move it up or down, and we apply the constraints to meet the requirements. And as we can see, it does meet our requirements and our constraints. Now, DesignForce also integrates powerful signal integrity analysis and topology planning features. It allows us to perform both automatic and interactive signal simulation. We can generate waveforms directly from the circuit design and perform important analysis like reflection and crosstalk, in addition to advanced analyses such as insertion loss, return loss, and TDR. As in Design Gateway, one of the most valuable features is the ability to conduct what-if analysis, and this lets us explore different design scenarios to optimize our design. So in the electrical editor, we select a transmission line, we open the configuration editor, and here we can change the width, for example, and see how it affects the impedance. We can see it change. We can also change other values such as thickness, edge factor. We can also play around with the layer thickness and materials. We perform here a parameter sweep for the conductor width to see how it affects the impedance, and we can see it going down when the conductor width goes up. We do the same for a differential pair where we can also add or change layers and experiment with different scenarios. We also do a parameter sweep, but this time for the dielectric thickness. And we can see here 3 different impedances because it's a differential transmission line. Now we can also, from our design, extract the signal and its component for analysis. So for example, here we do a parameter sweep for the length of the transmission line, and we can see the values here from 10 till 100 millimeters, and we see the result for each value, and we can compare them and decide which one works better for our design. We can also do parameter sweep for other components. Here we have grouped 2 different parameter sweeps, transmission lines and resistors. So we can see a wider range of different what-if scenarios. We can also definitely do parameter sweeps for the models, so we can determine which model fits our design requirements best. Here we can see the results for the different models, and also we can check which one performs best for our requirements and our design. Now, other than sweeps, we can also perform, for example, an eye diagram analysis, which is very important for the receiver to read the signal correctly. So here we can see an eye diagram, and to make it easier, we can also make and use eye masks that help us see if the eye opening is open enough for the signal to be correctly read. So here we can see the eye mask. And there are many other analysis and functions available in the electrical editor, but we sadly don't have time to cover them all today. DesignForce also includes powerful tools for power integrity and electromagnetic interference analysis. So it uses a numerical 2.5D frequency domain solver that allows for the analysis of irregular or complex power and ground shapes. And this is especially useful for nowadays for modern PCB designs where shapes are not always uniform. It also computes the AC impedance of power planes and displays impedance distribution, which helps designers identify weak points in the power network. Additionally, it performs DC analysis for things like IR drop and voltage at current or current distribution, ensuring that power is delivered efficiently across the board. There's also decoupling analysis, which evaluates the performance of decoupling capacitors. Virtual DC sources and virtual decoupling capacitors can also be used for what-if scenarios, so we can test changes before implementing them physically. And finally, it computes DC resistance, giving a complete picture of the board's electrical performance. So now we're directly starting with the DC analysis for our signal. We perform a voltage and current distribution simulation right now. So we can see how the power is distributed across the PCB design. In the analysis result viewer, we can adjust the scale to better visualize the results. And we are now looking at the voltage density distribution. And now we're moving on to the current distribution. So we can also play around with the scale to better see and read the results. Now for the current, we can also activate the current arrow, which shows arrows on the design to indicate how the current is flowing. So right now we can see the current going up, and then the blue area goes back down. So we can better visualize our current, how it's flowing. And to get an even clearer view, we can also switch to our 3D viewer to display the current flow in 3D. So if there's a few areas we want to better check, better see, we can definitely see them better in the 3D viewer. Now we select individual signal path so we can check their distribution again, but this helps us to see how the current behaves and helps us identify bottlenecks when available for specific signal paths. Now moving on to decaps, we can also see the power and ground mount percentage for each decap. And we took, for example, this one, which has a lower power mount. And we can see here that it's due to its large power connection surface. Another very helpful feature is the ability to add a virtual decap to the design. So this helps us test the effects of a decap before actually placing it and routing it and losing time over that and messing with our design. Now we're adding a decap, we're choosing the values. And we can see these are all our decaps in the design, and the virtual one is at the bottom of our list. And now we compute the PI distribution again. And we can see here at the location of the virtual decap, the impedance is lower than the surrounding areas, which is in green. The surrounding areas were in red. Now, last but certainly not least, we have the EMC Advisor EX, which is integrated into the CR-8000 design force to help identify and resolve electromagnetic compatibility and signal integrity issues. This tool provides built-in checks for SI and EMC specific rules, ensuring that designs meet performance standards. It features a user-friendly spreadsheet report which highlights errors and allows us to cross-probe directly to the layout, making error detection quick and easy. The tool covers 36 rules in 6 categories, and for each issue detected, there is access to design guidelines helping us understand and resolve the problem more efficiently and effectively. And lastly, it integrates NoiseKen results, providing real-world data for further analysis. So we first open the EMC Advisor, and we can see multiple issues, but we are focusing on the return path rule. And we can see multiple ENets that need attention, but we are again highlighting the first one. And we can also see here that there is no action taken yet. If we don't really understand why there is a warning, we can go and check the brief explanation for each rule. So for example, here we can see that the return path should be as close as possible to the signal net to minimize noise. We can use this information to go back and adjust the return path. Now we move on to the NoiseKen integration. So NoiseKen allows us to import actual noise measurement results into the software. Once imported, we align the result map with our PCB design, which we're doing right now. And then we can adjust the transparency to get a clearer view of the data and our design as overlaid on top of each other, so we can better understand the noise map. And using a probe, we can also focus on specific points on the map to check the noise levels at these locations. So for example, at the red area, we have a very high noise. At the yellow one, we can see on the right, it's going down. So the noise is not as strong as in the yellow and red areas. And we can see this is our problematic area. Now returning to the EMC, return path check. So we overlay the first return path into the NoiseKen map. Here we can see it, and this helps us correlate the detected noise with the return path and try to figure out how to reduce noise by improving the routing, for example. So you can see here, this is our main problematic area. Now this is after making changes to the design and remeasuring with NoiseKens. This is the new noise map that we imported, and we can see that the noise is way better and has significantly improved. We can also overlay our PI impedance for different layers. We can also overlay it for different frequencies, so we can see how it's changing, how it changed with the before and after the noise, and how it might be affecting the noise in a certain area. Now we compare both maps. The older one on the left and the updated one is on the right, which shows that we successfully reduced noise. And as we can see, the routing is also different. And now we check the return path, and by checking the return path in both designs, we can see clearly in the updated design, the routing has significantly improved, and this has helped us with having a quieter signal. And now focusing on the first ENAT, which is QD3, we can see the return path is way better routed, and this change directly has contributed to the reduction in noise. And our problematic area is now gone. And now, before moving to the NoiseKen part of the presentation, I would like to quickly go over any questions you guys have.
No questions so far, Romy.
Okay, thank you. So if there's no questions, I will let Mr. Sho Nakamura take over now.
All right, thank you very much, Romy. And it's a good, very nice presentation. Well, this is Sho Nakamura from NoiseKen. Today, I would like to give you an introduction about a space electromagnetic field visualization tool to help designers to conduct prototypes debugging, which is applicable to a single PCB board to a product as big as a vehicle. Okay, and this tool called is EPS. This EPS is an ideal tool to visualize invisible electromagnetic waves with NoiseKen's leading-edge technologies, enables designers to rapidly diagnose and solve EMC issues by quick noise source determination, hence dramatically reduce the design cycle. Well, we made this tool very easy to use. Everybody can help themselves, just simply apply the probes to the products. Then you can pinpoint out the EMC root causes and problems. Well, this is a configuration. You see that is very simple, a probe camera with a software and a spectrum analyzer. This is a real-time EMC debugging tool to gain immediate insight into the root causes of performance issues by analyzing the near-field results. The software detects locations of the probes by color discrimination through cameras. Image sensors offers real-time analysis of measured signal frequency, shows a heat map by overlapping the electromagnetic field strengths and real images of measured objects. Okay, why we use EPS? Benefits. The first one, dramatically reduce prototypes debugging time and costs of EMC countermeasures against RA compliance testing without using test sites. Second, accumulate EMC countermeasures know-how to continuously improve design efficiency. Third one, reinforce your design rules. And who and why, when to use the EPS? Well, the first case I would like to say it is before the compliance testing. Well, in order to pass the compliance testing, it is required to detect, characterize, and address unintended radiation or RF leakage. So the R&D engineers conduct pre-evaluation and take necessary measures before compliance testing, secure prototypes with reliable quality to be put into final compliance testing, and go for the mass production as scheduled. The first one is usually used after the compliance testing. Sometimes if when you receive the fail report from the lab, well, sometimes we can know the EMI problem source with the source, but most of the time it is kind of difficult and taking a long time to define the source. By using EPS, visualize the root cause source of potential EMC and EMI problems and show you where you have to focus on to continue your countermeasures. Okay, well, this is some voice from customers. Well, one customer, they said, told us that before they need 4 time to get their products to the lab house in order to pass the final compliance testing. Now, well, they still need 2 times, but reduced a lot manpowers. And another customer told us everybody is able to do debugging by themselves. Even untrained or inexperienced engineers, now they can help themselves, not always ask for help from a trained or skillful engineers. They can debug by themselves. And another customer told us all the data is stored and reviewed is much more convenient, and all the actions you can share in the team. Everybody share the history of the improvement actions. And from these slides onwards, I would like to introduce the major functions of this visualization system. First one, 3-dimensional indication, not only the frequency amplitude, but also a time domain. Second one, easy and efficient comparison before and after the countermeasures. The third one, save measured data to accumulate technical improved know-how within the team. Okay, well, this is the 3-dimensional indication. Maybe it's better for me to give you an actual demo to see how this will work, right? Okay, I think you can see my hand. Well, this is a demo board, a camera at the top of the board, and this is the near field probe and get a color, and the camera will catch the color. Okay, here you just simply press the start button, then this system will automatically catch the signals, the noise from the boards. You can see the color will change because this is a max hold system. The software will hold the max point at each location scanned throughout the frequency range. All right, now we finished scanning. Well, you can see here's the red color shows a stronger electric field on the boards. This dot will automatically stay at the highest field strength level. Here is the source that generate the strongest electric field strength. If you move this dot to other place, you can see the spectrum under there. Okay, not much change. It's all the signal remains at the normal. But here you can see some spikes here that tells you this noise is rare noise occurs here. Okay, and you might also want to specify the frequency range. For example, this dot state here, it tells you you have 22 megahertz and you see 62 dB microvolts. You might want to see more at this frequency range, say from 15 to 30. Okay, then you specify the frequency range you set from 15 megahertz to 30 megahertz. Then we'll give you a more specific analyze here, tell you, okay, and this is the area you have to focus on with your prototype here. And of course, you can enlarge anytime this frequency range. You can adjust according to your demands. All right, and go back to this map, and here you might tells you this is the highest stronger electric field strength occurred there. You might want to see more details what is under there, and if that's the case, there's a time domain frequency say first. This will give you another window to provide you a time domain analysis. Just simply put the probe on the top where you want to see more details there, and here just simply press the start button, and this tool will automatically run for you, tell you the strength when the time passing by. All right, and now today, just for demo, we set 20 seconds, and this system can support up to 999 seconds. Okay, so you move this bar, you can see all the strengths at each time. Say if here you see at 1000 microseconds, you see 55 dB microvolts. You move to other place. Say you see here, you got a 6000 microseconds. You see another 55, 54. You move this bar, can tell you each strength level at each time. Okay, well, this is a tester board. So you might, if you see, okay, every 10 seconds, it looks like there's some unwanted noise per 10 seconds. So you might, this will give you more data. You might want to see more what's happened at this area. Right? Okay, after you scan your data, of course, you can save the data. Give you an example. If you want to save as CSV data, just click CSV here and will be saved. And at the same time, you might also want to save the image, record your image, right? And let's see, this is the data we just now exported. Okay. So give you each location at what frequency level you got, how strong the strength there. And at the same time, you might also want to add the image to your SCV report and gives you all the distribution. Each point at what frequency level you get how strong they be there, right? All right, let's go back to the presentation material. So this is another very useful functions, very easy efficiency comparison before and after design improvement countermeasures. Well, just now Romy has presented the details. I'm not going to talk more about these details. Before you make countermeasures, you measure again. After you made the countermeasure, you measure again, and this system will give you a differential image display, tell you, okay, you solved the problems at this area. At this area, maybe you need more additional improvement or something. And well, all the improvement actions required is saved, measured data, and you can accumulate technical improvement know-how within the team, share the experience. And this slide is just now Romy had also explained. We collaborate with Zuken CR-8000, the EMC advisor. The actual measured results produced by this EPS visualization system can be laid over to the design data of the CR-8000 and enhancing your EMC design rules. Okay, there's a very big number of useful functions offers virus analysis. Superimposed display offers easy noise level comparison. Check the difference between the designated point and each peak point. And density display expands your analysis ranges. You can check the noise occurrence, frequency, and the amplitude at the measured frequency. And of course, you can record the countermeasures actions at each checkpoint and share within the team. Okay, this is a summary about the advantage of the EPS debug electromagnetic wave quickly and conveniently. Check countermeasure fact in real time, enable countermeasure from a single PCB board to a whole product. Easy comparison before and after countermeasure, easy debugging report, visualize design rule and accumulate design experience, reduce efforts of use anechoic chambers. So by you checking, take countermeasure, accumulate experience, and keep optimize the design cycle. Well, this pie shows based on our record, 27% to those automotive industries and 23% to the industrial industries, and they shared 50% of the market. Well, this is some major customers who introduced the EPS system for their prototype debugging. And from this slide onwards, I would like to have some questions and feedbacks. Well, this is some frequently asked questions from the market. What is the image division size for measuring? Well, it's from 10 pixel to 160 pixel. This is the image. If it's a small PC board, then you select smaller pixel. And if it's a big product like a vehicle, you select bigger pixels. And another question is what is the applicable frequency range for measuring? Well, actually, this tool can support from 1 Hz to over 10 gigahertz because it relies on the specification of the probes and the spectrum analyzer according to your demand. Well, the last one, what is the applicable spectrum analyzer? Well, this system actually supports a wide variety of standard compliant spectrum analyzer drivers. Well, those are very common spectrum analyzer at the market: Rohde & Schwarz, Keysight, Tektronix. Well, if your spectrum analyzer is not on the list, well, simply just tell us, see whether we can made a driver for you. Okay, thank you very much. That's all my presentation for today. Now I would like to hand back to Romy, see if you have additional questions to Romy for the Zuken CAD tool. Thank you.
Thank you very much for this great presentation, Nakamura-san. So I think we got a very good overview on functionality of NoiseKen and how easily you can use this and very fast, how fast you can use it to run an EMC analysis during the design phase for EMC test laboratory. Thanks again for this presentation. Also, thanks for Romy to give us an overview about functionalities, signal integrity functionalities in CR-8000